Everyone, this is Lab 5, which is Magnetic Braking with Faraday by Kayla Kerniel. So to introduce, the purpose of this lab is to understand Faraday's law with time-varying magnetic fields related to Curry electric fields through observing how a falling bar magnet is the source of an external field through an aluminum tube, which undergoes an induced current. The fundamental physical principles include the Biot-Savart law, Faraday's law, Ohm's law, and magnetic force, with Faraday's law and Ohm's law pictured on this slide. The main physics ideas include that the bar magnet acts as a magnetic dipole, and that the aluminum foil tube undergoes an induced current due to the falling magnet, and induced current is pictured on this slide. So the results overview, our computational was 1.069 seconds, experimental was 1.512 seconds, and then there is a photo of the output where the magnet is still falling through the aluminum foil roll. So for the experiment, we are assuming that air resistance is negligible, and gravity and the magnetic forces are the only forces acting on our system, the system being the magnet and aluminum foil roll, and everything else being the surroundings. The initial conditions is that the bar magnet was poised above the entrance of the aluminum foil roll. So there is a photo of that initial condition. We first used the magnometer app in order to mark the north pole of the bar magnet, and then holding the roll vertically with another teammate filming the entire length of the tube. We then held the bottom of the tube in order to not let the magnet fall, timing and videoing dropping the magnet through the aluminum foil roll, as seen there. Here is the after, where we caught the magnet, and then we proceeded to complete this same experiment 5 different times in order to get an average time it takes the magnet to fall through the tube. So our checkpoint questions. Why can't we use a ferrous tube? A ferrous tube would have magnetic properties that would cause an induced magnetic field from the iron, which would then change the outcome of the falling magnet. What happens to the magnet? How does this compare to a magnet falling in free space without a tube? A magnet falling in free space without a tube falls faster, and the magnet falling through the tube is slower due to the upper magnetic force caused by the current in the tube. So here is our data, all 5 trials. The length, radius, width, and magnetic dipole moment from Lab 3 are all tabulated here. So starting with our coding, the physical constants were first defined and the graph was initialized, and then we created the tube of aluminum foil, putting in the geometries that I showed you just then. Next, the numerical parameters of the simulation were defined, and then created the tube of aluminum foil as a series of rings. Again, this section was not edited. We then created the bar magnet, which was edited, and I did do some recalculations of the magnetic dipole moment in order to make it more accurate. We then visualized the bar magnet. Initial conditions were then defined as the velocity is 0 at the start, and then we created a function to calculate the magnetic field of the bar magnet, which is very similar to Lab 3. We then created a function to calculate the actual magnetic flux through each ring due to the falling magnet, which is seen in the function here. Then the simulation loop was created, and we did not edit this largely, except for the gravitational force, which is of course negative mg in the y direction. We then calculated the magnetic force from the tube on the magnet, computing d flux dt for the ring due to the falling magnet, and then we edited this to calculate the current, which is of course the d flux dt divided by the resistance. We then colored each ring according to the current. So we then edited these 4 lines to compute the typical B field at each ring, which you can see the edits shown here. And then we calculated the magnetic force on the magnet, calculated the net force, which is of course the gravitational force plus the magnetic force, and then we updated the magnet's velocity and position. This was using Newton's second law, as seen here. So here's the actual output graph, and the time in seconds was 1.069, as I showed you earlier, as well as the visualization at the very end. So interpreting the simulation, the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise and which counterclockwise? So the red current corresponds to counterclockwise, and the blue corresponds to clockwise. This is known because of Lenz's law. What happens to the dynamics of the system when you flip the magnetic around? When you flip the magnet around, all it does is flip the direction of the current, so the magnet will still experience the same slow fall through and the same magnetic force as before. So how does the total time in the tube of the real-world system compare to that of the computational system? How might the computational system be made more accurate? The computational system did happen faster than it did in the real world, and it could be made more accurate by splitting the tube into individual rings to recalculate the magnetic dipole moment. There's definitely some discrepancy in values, likely due to this different dipole moment. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So it shows that the forces are unbalanced because the velocity is not constant, and then they begin to balance as the velocity becomes constant, which shows that there was a slowing in the fall. And then when it completes the fall, the gravitational force is then larger than the magnetic force, ending in a non-constant area of the graph. To discuss this, similarities and differences, the code lacks environmental aspects and sources of error as discussed below. And the code also inputs a magnetic dipole moment that may not be accurate to how it was in the real world. So possible sources of error, air resistance could have been considered. The magnetic dipole moment should be recalculated with additional accuracy. Human error, as the magnet would occasionally have issues getting stuck in the tube, which had this gone unnoticed, would have increased the time. So what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? The induced current in the tube would be much greater because of Ohm's law, thus creating a greater magnetic force and potentially stopping the magnet from falling at all due to being greater than the gravitational force. What if holes or slots were cut into the tube? How would this affect the currents? They would lessen as the current would be disrupted, causing a smaller magnet force and a faster fall for the magnet. So to conclude this, an upward magnetic force acts on the falling bar magnet due to the induced current, and this can be done experimentally and computationally. Thank you.